Okay there, students of chemistry. This is a quick reminder about acids and bases. Before you listen to this recording, you should print off the notes that go with this. There is what's this? There is a page of practice problems that you're going to want to print. So we've talked about acids and bases last year, of course, in honors chemistry. And then when we were doing acid-base reactions, we also touched on them there. So there was a reminder of definitions of acids and bases also when we predicted products for acid-base reactions. So here's the third reminder about acid and base definitions. We have the Arrhenius definition, which says that acids make hydronium and bases make hydroxide. And this is where we get kind of our pH calculations, right, from the autoionization of water. And then we have the Bronsted-Lowry definition, which is a little bit broader. Acids donate protons or hydrogen ions, whereas bases accept protons or hydrogen ions. So conjugates, right, are formed, those species that are formed once that hydrogen is donated or accepted. And we know that conjugate bases come from acids, and conjugate acids come from bases. One thing we may not have mentioned to this point is that weak acids will always have a strong conjugate base. Like water, H2O is a weak acid, and its is a weak base, and its conjugate acid H3O plus is a strong acid. I know I just threw that acid in there, that base in there instead of an acid. So conjugates are generally negative ions, and therefore have the ability to accept a hydrogen, which is why we call them a base. So it really just depends on how strong the acid that it is with is, whether it's going to take that hydrogen or not. And then, of course, conjugate acids, the species when that is formed after that proton is accepted. So once that base accepts a proton, now it has this hydrogen ion or proton that it can give away. And again, strong form weak. So some substances that are amphoteric, meaning that they can act as both an acid or a base, that would be any substance that is a negative ion that also has a hydrogen to donate. And remember that an acetic hydrogen is in the front of the compound formula. So if you have acetate ion, for example, that is a base, C2H3O2, but it cannot act as an acid. That hydrogen is incorporated in the structure of the ion in a covalent bond and is not able to be donated. So example there, the bicarbonate ion is a great little amphoteric substance. It has a hydrogen to donate if it's with a strong enough base, and it's negative, so if it's with a strong enough acid, it can accept that hydrogen. So just a reminder that conjugate bases, if we have the bisulfate ion, for example, here, its conjugate base is once that hydrogen goes away is the sulfate 2- ion, which is a better base than the bisulfate ion. It's got that charge of -2. It's going to attract a hydrogen better than the bisulfate. Of course, hydrochloric acid, being a strong acid, has the weak conjugate chloride conjugate base. Water as an acid is a weak acid and therefore has the very strong conjugate of hydroxide. Bisulfate ion acting as a base is going to accept a hydrogen and make sulfuric acid. The sulfide ion is a pretty strong base. It has two conjugates. The first conjugate would be that hydrogen sulfide, and the second conjugate would be sulfuric acid. I'm sorry, hydrosulfuric acid. Ammonia is a weak base, and its conjugate, ammonium, is decently strong. We've got to be careful with that because, you know, there's a fine line between what's considered a good acid or a bad acid, or a good base or a bad base. It really just depends on what's reacting with it. So just remember your pH calculations. We know that water, notice the double arrows, is in an equilibrium with hydronium and hydroxide ions. And the equilibrium constant for water, like if we did the law of mass action to get the equilibrium constant expression. K would equal concentration of hydroxide times concentration of hydronium, right? And then we would throw out the liquid water. That value is 1 times 10 to the negative 14, which is kind of where we get this pH scale, which means that when hydronium and hydroxide are in equal concentrations, that equilibrium concentration is 1 times 10 to the negative 7, which is where we get a neutral solution of pH 7. So in a neutral solution, hydronium equals hydroxide. In an acidic solution, there's more acid than base, so hydronium is greater than hydroxide. And then in any basic solution, the hydroxide ion will be present in a larger quantity. Oh, oops. So if we have a solution that is has a hydroxide ion concentration of 7.8 times 10 to the negative 6, we don't even have to do any calculations here to figure out that this solution, to figure out whether the solution is acidic, basic, or neutral. We know that 7.8 times 10 to the negative 6 is a larger number than 1 times 10 to the negative 7. And therefore the hydroxide is larger in this solution than it is in water, meaning that this solution is going to be basic. And we can calculate the hydronium ion concentration by using the Kw for water. So Kw equals concentration of hydronium times concentration of hydroxide. So that's 1 times 10 to the negative 14 equals hydronium concentration times 7.8 times 10 to the negative 6. And I don't have a calculator, so let me get one here. So that hydronium concentration is 1.28 times 10 to the negative 9. Using the correct significant digits, that would be 1.3 times 10 to the negative 9 molar. So we know that pH is a measurement of acidity. It is the opposite of the logarithm of hydronium. So if we wanted to know the pH of our solution here, of course, we just do negative log of our 1.3 times 10 to the negative 9, which is going to give us a pH of 8.8. 8.89. Two significant digits. The significant digits in a logarithm are found in the decimal places. So that number does not have 3 significant digits. That pH, as written, has 2 significant digits. Right? So remember that because acids make hydronium, pH is a measure of acidity. Because bases make hydroxide, pOH is a measure of alkalinity. So we remember these formulas. We looked at them last year. Remember that we can always use exponential forms to go from a pH to a hydronium concentration, or a pOH to a hydroxide concentration. Oops, I just saw that. And then really this pH plus pOH equals 14 is really just the negative log of hydronium plus the negative log of hydroxide equals the negative log of 1 times 10 to the negative 14. That's just taking the logarithm of all of those numbers from the Kw of water. So the only difference between a strong acid and a weak acid is that a weak acid reaches equilibrium and a strong acid goes to completion. So whatever the concentration of our acid is, that is also going to be the concentration of our hydronium ion. However, that is not true with the weak acid. If we're figuring out the pH of a weak acid, we'll need to figure out those equilibrium concentrations using an ice chart. So these are what we're going to look at in the next couple units. Today we're going to look at calculations of strong acids and bases, pHs, just like we did before. And we're going to do some mixtures. What happens when we mix a strong acid and a strong base? Of course, that reaction goes to completion and becomes is a neutralization reaction. What happens when we mix weak acids with strong acids and weak bases with strong bases? Salt hydrolysis is something we're also going to look at. Salts have a nature, whether they are acidic, basic, or neutral. And then when we start mixing things together, when you have a strong acid and a weak acid, remember that hydronium comes from the strong acid only. The weak acid is just like adding water to it. So the same thing with a base, except that this time it's hydroxide coming from the strong base only. And then adding the weak base is just like diluting it. Strong acid, acid. Well, those hydronium concentrations, or hydronium moles actually, will be additive. So we add the moles together and divide by the total volume. Same thing with the base. The hydroxide moles are additive, and then we add our moles together and divide by the total volume to get the concentration. And then a strong acid and a strong base, that's neutralization. If they are acting in equal mole ratios, then the acidity of the solution will depend on the salt that is formed. If they are not, the acidity of the solution will depend on what is left over. And then we have these mixtures of weak acids and weak bases, or weak acids and a strong base. So this is really a weak acid mixed with its conjugate, or a weak base and a strong acid, and then some salts. What happens if we have salts that we mix together? And when all that happens, we get buffers. And we'll spend several days doing calculations on buffers. Okay, so quickly a reminder about pH calculations. Just really quick, so this should correspond to the note page that was provided for you to print, and then you will do those problems at the bottom of the page by yourself. So if we have hydrochloric acid, right, so we know that this is going to make hydronium. We know that this is a strong acid, so the concentration of the acid is equal to the concentration of hydronium, and to get the pH, the opposite of the logarithm of hydronium ion concentration. Oops, it's 0.0025. And the pH is 2.60. We've got 2 significant digits in our concentration, and therefore 2 decimal places in our pH. If we want to know the pOH, we know that we can use the formula pH plus pOH equals 14. So therefore pH is equal to 14 minus the pH. I'm sorry, pOH is equal to 14 minus the pH. So 14 minus 2.6, 11.40 for the pOH. And then 2 ways we can get the hydroxide ion concentration. We can either use the kW for water, which says hydronium concentration times hydroxide concentration equals 1 times 10 to the, I'll put another 0 in there, negative 14. I tend to use the exponential form, so I'll do 10 raised to the power of negative 11.40 to get the hydroxide concentration. Either way you choose, it's going to give you the correct answer. It might be off a little bit with significant digits or what have you. So we're looking at a concentration with 2 significant digits of 1.1 times 10 to the negative 5 molar. So reminder about bases. Here's the thing about calcium hydroxide. That's a family 2A base. So the concentration of hydroxide, based on the formula, is double the concentration of calcium hydroxide. So here the hydroxide concentration is 0.0090. And then, of course, from that, because this is a base, we are not going to calculate pH. We're going to calculate pOH. Bases make hydroxide. So the opposite of the logarithm of 0.0090. Two significant digits means our pOH is going to have 2 decimal places, which leads us to a pOH of 2.05. And therefore the pH is 14 minus 2.05. That gives us a pH of 11.95. And then the hydronium concentration, I'll solve this one the other way, is equal to, if we're using the kW for water, 1 times 10 to the negative 14 divided by 0.0090. And that's 1.1 times 10 to the negative 12. Okay, let's consider these mixtures. If we're going to have these 4 solutions, let's calculate the pH of each of those. I'm going to skip that because I think you can do that by yourself there. And we're going to do this just the strong acids and bases. So this one, HNO2, that'd be nitrous acid, that's weak. Ammonia is weak. Calcium hydroxide is strong. Nitric acid is strong. Hydrochloric and sodium hydroxide. So take a minute to calculate those pHs. Go ahead and pause the recording there. And then when you have it, check your answer. All right, then, if you will check your pHs for the acids and bases that are listed above. Now we're going to start mixing them together. So calculate the pH of a mixture of hydrochloric acid and nitric acid. So the first thing you need to recognize here is that these are both strong acids. And because they're strong acids, the moles of hydronium are additive. The other slide said that the solution of hydrochloric acid was 0.2 molar. And the solution of nitric acid was 0.04 molar. So we'll get moles. For the hydrochloric acid, 40 milliliters times 0.020 millimoles per milliliter. Right? That's going to give us moles of hydronium from the hydrochloric acid. And then do the same thing with the nitric acid. Let's see, we have 20 milliliters of 0.04 molar nitric acid. And that's going to give us moles of hydronium. Once we have our moles of hydronium, we'll divide that by the total volume and then calculate pH. So this is 0.8 millimoles. And 0.8 millimoles. We'll add these together, and that's going to give us 1.6 millimoles divided by the total volume, 40 plus 20, is 60 milliliters. And because each of those are strong acids, this concentration is the concentration of hydronium, and therefore pH equals negative log of 1.6 divided by 60. 2 significant digits, which means we're going to have 2 decimal places in our pH, so the pH is 1.57. Okay, now we're mixing sodium hydroxide and ammonia. So notice that this is a strong base mixed with a weak base. Whenever you're approaching these problems, you first have to identify your substances. Is it an acid? Is it a base? If it's an acid, is it a strong acid? Or is it if it's a base, is it a strong or a weak base? So the other slide said the sodium hydroxide concentration was 0.02 molar. And the ammonia concentration was 0.04 molar. So here's the thing, when you're mixing a strong with a weak, the moles of hydronium or hydroxide come from the strong only. The weak is just like adding water to it. So we may as well have said this problem, you know, what's the concentration of hydroxide, 40 milliliters of sodium hydroxide, if we add 20 milliliters of water to it. So if we want the moles, 40 milliliters times 0.02 millimoles per milliliter, that's going to give us the hydroxide concentration and the sodium hydroxide concentration. But because it's a 1-to-1 ratio between sodium hydroxide and hydroxide, we'll have the hydroxide concentration as well. That's going to give us 0.8 millimoles. And we'll divide that by the total volume. 40 plus 20 is 60 milliliters. And that will be our hydroxide concentration. So if we want the pH of this solution, pH is equal to 14 minus an opposite of the logarithm of 0.8 over 60. And that pH is 12.12 with 2 significant digits in the pH. Remember that the significant digits are found in the decimal places on a pH. Okay, so now here we have hydrochloric acid mixed with sodium hydroxide. These are each 0.02 molar, and that's a strong acid. This is 0.02 molar. I'm getting that from the first slide. And this is a strong base. Anytime you have an acid with a base, whether it is strong or weak, that reaction will go to completion. So we have to write the reactants and actually react those. All acid-base reactions, strong or weak, go to completion. So before reaction, during reaction, after reaction. So what we need to do when we have an acid and base actually reacting is see what's left over. See what we have when we're done. So we'll get moles. 40 times 0.02 is 0.8 millimoles of hydrochloric acid. And 20 times 0.02 is 0.4 millimoles of sodium hydroxide. Determine the limiting reagent. We know that with a 1-to-1 mole ratio, whichever one is smallest will be the limiting reagent. So hydroxide goes to 0. Don't forget to show your mole ratio, even though it's a 1-to-1. So we can see that the sodium hydroxide goes to 0, and we have 0.4 millimoles of hydrochloric acid after the reaction. We have 0.4 millimoles of water, and we have 0.4 millimoles of the salt, sodium chloride. So from here we determine, hey, which one of those is going to make a significant amount of hydronium or hydroxide? And if you guess the acid, da-da-da-da, you're right. So to get the concentration of hydronium, 0.4 millimoles divided by the total volume of the reaction mixture, which is 60 milliliters. So therefore pH equals the opposite of the logarithm of 0.4 divided by 60. And the pH is 2.18 to 2 significant digits. Okay, so there you have it. That is what I expect you to do at this point. So just to be clear, what you should be able to do after this is, know your definitions of acids and bases. You should be able to calculate pH for strong acids and strong bases. You should be able to calculate pHs of mixtures, whether it is a strong acid and a strong acid, or strong and strong, or a weak and strong, or a acid mixed with a base. And that's what those problems are that you will need to have done before I see you again in class. Okay, thanks. Sorry for the length.